Okay, so in the last video, we started off talking about energy and what is meant by energy, and we talked about some different types of energy, and we also looked at some simulations focusing on some of the key concepts in this unit, namely the idea of conservation of energy, how energy is basically this thing where there's different types of it, and the total amount of energy in a system can't change, but it can change from one form to another form. Okay, and so when we're doing problems, you need to be able to identify what type of energy is involved in a given situation. And so that involves relying on context clues. Okay, and so we have this checklist here that I've created to help you figure out what type of energy or energies an object has at any given moment. Okay, so as you're doing problems throughout this unit, this is the mental checklist that you will need to go through as you are trying to figure out what type of energy or energies does an object have. Okay, so is the object moving? Okay, so if it's moving, it has kinetic energy automatically. If it's not moving, it doesn't have kinetic energy. And remember, for kinetic energy, we write EK. Number two, is there a spring or a rubber band involved, something stretchy? If so, then it has elastic potential energy. So remember, potential energy is stored energy, and elastic is something stored in like a spring or rubber band. Is there height above the ground? Okay, does the object have a height above the ground? If it does, it has gravitational potential energy, and for that we write Eg. And I do want to point out it's possible to have more than one of these types at the same time. Okay, so that's why you have to run through this whole checklist. Is there friction? Okay, if there's friction in a problem and the object is moving, then it is going to produce heat. It's going to produce thermal energy. And so for thermal energy, we're going to write ETH for thermal energy. Okay, that's heat. Is there energy added from a source outside the system? There must be work being done. Now, work is not a type of energy, it's a transfer of energy to or from an object. We'll talk more about that later. Okay, and then finally, is there some type of battery or fuel? If so, then we have chemical energy, and I'm going to write EC for chemical energy. Okay, and so this is the mental checklist that you will need to run through as trying to figure out what type of energy an object has. All right, and so make sure you have this in your notes because you're going to be using this all the time. And the next couple slides, we're just going to be doing some examples, writing down what type of energy or energies an object has, and then writing conservation of energy equations like we'll see. Okay, so pause here, add this to your notes, and then we'll move on. Okay, so as I said before, um, when you're reading a problem, you need to be able to use that mental checklist to figure out what type of energy an object has. Now, in most problems, there's going to be a beginning state and an ending state. Okay, an initial energy state and a final energy state. Okay, like a beginning and an end. Now, some problems are going to have more than just a beginning and an end. They might have like a middle state. Okay, but most situations are going to have like an initial, what is the initial energy and what is the final energy? Now, at each of those states, you need to figure out what type of energy or energies does the object have. And the way you do that is you run through that mental checklist that we just saw. Okay, so as we're doing the examples on the next slide, in order for you to figure out what type of energy there is, you need to go through this mental checklist. Here it is. That's why I suggested you add it to your notes at both the initial state and the final state. Okay, so we'll do some examples so you can see what that means. The last thing I want to say is to remember, and this is one of the key concepts in this entire unit, that the total amount of energy in a system is always conserved. This is called conservation of energy. It's the like big key concept in this unit. The total amount of energy in a system is always conserved, but energy can change from one form to another form. And by conserved, I mean stays the same. In other words, the other way of saying that is that the initial energy and the final energy have to be equal to each other because the total amount doesn't change, it just changes different form. Okay, so we're going to do some examples so you can understand this concept better, and then we'll be done with the video. Okay, so let's take a look at example 1. Okay, so example 1 says, a car starts from rest and speeds up until it's cruising along a flat highway road. Okay, what type or types of energy does the car have in its initial state? Okay, so the initial state of the car is It's at rest. Okay, so in your mind, to answer this question, you need to run through that mental checklist. Is the object moving? Well, no, because it starts from rest. Okay, is there a spring or rubber band involved? No, definitely not. Okay, is there height above the ground? No, because the car is like on the road. It's not like on a hill or something, so there's no height above the ground. Is there is there friction? Okay, well there could be friction, but because the object starts from rest, there's no thermal energy, at least not yet. All right. Um, is there any like outside energy being added? No. Okay, so if you run through your mental checklist, the only energy that you should find in the initial state is chemical energy, EC. Now, why chemical energy? Well, because the car has gas in it, and the gas provides chemical energy for the car. Now, let's think about the final state. What type or types of energy does the car have in its final state? So what do we mean by the final state of the car? Well, it says the car starts from rest and then speeds up until it's cruising along a flat highway road. Okay, so again, we have to run through this mental checklist. Is the car moving in its final state? Yes, that's what it says. Okay, so it definitely has at least kinetic energy. Is there a spring or rubber band? No. Is there height above the ground? No, because it says it's a flat road. Is there is there friction? Because if it's moving with friction, it's probably going to make thermal energy. Okay, and it doesn't say there's friction, but let's just assume for the sake of argument that there is in fact um, friction, which means there's going to be thermal energy. Okay, so now we have two types of energy in the final state. We have kinetic energy and thermal energy. There's no energy being added from any outside source, and so those are the only two energies that we have. Okay, let's just assume all the chemical energy is used up. Let's say the car is running out of gas. The last question says write an equation that represents this transformation of energy. So what that looks like would be in the initial state we have EC, and the key concept of conservation of energy is that the initial energy and the final energy are equal to each other. So the way I'm going to write that is EC equals EK plus ETH. And that's it. Okay, that is our energy transformation equation. Okay, the chemical energy in the car gets used up and turns into kinetic energy and also a little bit of thermal energy. Okay, some heat from the friction. So that is it for example 1. Pause it there if you need to look at some more. Okay, example 2. It says a boy playing with a rubber ball or a rubber band pulls it back and releases it so it shoots straight up into the air. At its highest point, the rubber band stops moving for a split second. Okay, we've seen that before. Now the first question says, what type or types of energy does the rubber band have before it's released? Okay, so before it's released, let's run through our mental checklist. Before it is released, is the rubber band moving? No, because it hasn't been released yet. Is there a spring or rubber band? Yes, and it's stretched out, so that means we have elastic potential energy. Is there height above the ground? No, not yet. Now it's shot up into the air, but not before it's released. Is there friction? Okay, no, there's no friction in the air. There's no force from an outside source, and there's no chemical energy because there's not like fuel or gas or anything. Okay, so what type of energy does a rubber band have before it's released? Just elastic potential energy, EE. What type or types of energy does a rubber band have after it has been released, but before it reaches its highest point? Okay, so again, you run through your mental checklist. Is the rubber band moving at this point? Well, it's already been shot up into the air. It hasn't reached its highest point, so that means yes, it is moving. Does it have, is there a spring or rubber band? Yeah, but it's been released, and if it's been released, there's no more elastic potential energy. Okay, so there's no EE. Does it have height above the ground? Yeah, because it was shot up into the air. Okay, so yeah, it has some EG, gravitational potential energy. Is there friction? No. At least it doesn't say there's friction. And friction you don't usually have in the air, you have it like on a surface. Okay? There's no chemical energy, there's no work being done. So those are the only two types of energy we have. And then the last question says, what type or types of energy does the rubber band have after it reaches its highest point. And that part is important because it says in the problem, at its highest point, the rubber band stops moving. Okay, let's go through our mental checklist one more time. Is the rubber band moving? No. Okay. Is there elastic potential energy? Not anymore because it's not stretched out anymore. Okay. Is there height above the ground? Yes. All right. Is there friction? No. No thermal energy. No work done. No chemical energy. So what does our transformation of energy equation look like? Okay. So we start off with only elastic potential energy. In the middle state, we have a combination of kinetic and potential. It's actually 50-50. And when you were playing around with the energy skate park, you probably saw like there was like a pie graph, and sometimes there was kinetic, and sometimes there was potential, and sometimes there was like a split between the two. Okay, and then at the final state, all we have is the gravitational potential energy. Okay, so what happens to the rubber band is the boy pulls it back, stores up elastic potential energy, lets it go. That amount of elastic potential energy gets transformed into kinetic energy and potential energy as it goes up. Okay, and then as it keeps going up, it loses kinetic energy, and then all of that kinetic energy goes into gravitational potential energy at the highest point, and then it starts to fall back down again, and the energy turns back into kinetic energy. Okay, so that is it for example 2. Pause there if you need to look at that some more. Okay, so I want you to try to do example 3 on your own. Okay, so read example 3 carefully. Try to answer this question on your own. Okay, and so what you should have gotten is that the initial energy state is only gravitational potential energy, because before the girl releases a penny, it's not moving. Halfway when it's fallen, it has a combination of kinetic and gravitational potential energy. Right before it hits the ground, it has no more height, so all it has is kinetic energy. And then after it hits the ground, that one is kind of tricky actually. After it hits the ground, all that energy gets turned into heat actually. Okay, so there's not friction per se, but when it hits the ground, it gives all that energy up into thermal energy, into heat. And if you've ever like taken a hammer, like hammered on the ground for a while, you felt the hammer get warm and you felt the ground get warm. And so that's where the energy goes. Okay, so that last bit was a little bit tricky. Okay, but that's what the transformation of energy equation should look like. Okay, so pause there if you need to look at that some more. Okay, and then just one more example. Try to do example 4 on your own. Okay, so when the box is released from rest, that means it has no kinetic energy to start with. If you run through your mental checklist, the only energy it should have at the beginning is e.g. gravitational potential energy because it has height above the ground. In the final state, at the bottom of the ramp down here, there's no more height, so there's no more EG, but the box is moving because it's been sliding. Okay, so it definitely has EK, but also if there is friction, there's also going to be thermal energy. So in other words, the box and the ramp are going to heat up slightly. Okay, so there's EK and E thermal at the bottom of the ramp. And so that conservation of energy equation would look like EG equals EK plus E thermal. Okay, so hopefully you have a better understanding of different types of energy and how to write like energy conservation equations. Okay, as always, please let me know if you have any questions, and I'll see you guys in the next video.